Hey everyone, how are you? Today I will fine-tune a BERT model for multi-class classification with custom dataset. And the dataset has been compiled from Turkish newspapers and consists of 7 categories. Let's start. Alright, first you need to install your transformer and datasets from Hugging Face. And I'll be using PyTorch here. So first, let's quickly read the dataset. It's a very small CSV file and it's in Kaggle already from a Turkish newspaper. I'll put a link definitely in the description of the video. So you can see that the categories are like this: technology, sport, dunya, etc. And the corresponding text is here. So the whole purpose of this fine tuning is that the model will be trained on these dataset. And then I will pass a new text and the model will predict the categories of that text. So it's a multi-class classification problem and I have 7 classes. So if you just take the unique values from the categories column, you will see there are 7 of them: technology, sport, dunya, kultur, economy, saglik, and siyaset. I don't even know some of the words meaning here. All right, now I need to build the dictionary of ID to label and label to ID because these are required for our Hugging Face training pipeline. So in this cell, that's exactly what I'm doing. I'm just enumerating over the labels, that is unique labels, and taking their ID and key and making 2 dictionaries out of that. The first one is ID to label, which is something like this. That is, I will have individual numeric keys and the corresponding label. So why do you need this kind of things is because in NLP tasks, especially those involving classification problems, ID to label and label to ID dictionaries are used to map class labels to integer IDs and vice versa. These mappings are essential for various stages of the NLP pipeline, such as data preprocessing, model training, and evaluation. So for example, in data preprocessing, in order to feed the text data into an NLP model, the text must first be tokenized and then converted into numerical values. Similarly, class labels must also be transformed into numerical representation. The label to ID dictionary helps in converting the original class labels into integer IDs. And during the model training, the NLP models usually output probability distribution over classes as their predictions. So during training, the model's prediction are compared against the ground truth labels, which have been converted to integer IDs to compute the loss and optimize the model parameters accordingly. And also during model evaluation and interpretation, once a model has been trained, its prediction, that is in the form of integer IDs, need to be mapped back to their original class labels to make the result interpretable. So the ID to label dictionary and also the label to ID dictionary is used to perform this kind of conversions. And specifically in this case, so right here, the pre-trained model that I will be using is BERT for sequence classification. And that needs these exact mapping of ID to labels and label to IDs in dictionary form as 2 attributes to be passed when the model is initialized. Hence, before you start training your model, create these 2 dictionary mapping of the expected IDs to their labels with ID to label and label to ID. And this is pretty much their output. That's the format you will need. This is for label to IDs, that is, each label is mapped to an ID. And this is for ID to label. All right, now I need to create a new column and the next I will need to create a new column to represent the categories in numerical form. And in below right here, I am doing it manually, but I could have also done it with pd.factorize, that is a particular factorize method which is inbuilt in pandas. So this is commented out code, but I'm putting it just to show that how it could be done with a single line of code. So this pandas factorize method is used for encoding categorical variables as integers. It assigns a unique integer value to each distinct category in a given series or data frame, effectively transforming non-numeric data into numeric values. And so that code is just commented out, but the way that I'm doing it is rather manually. So I am making use of these map method and then applying this map method on the category column in my data frame, and then a lambda function which will strip each value of this category column, because these category column string values have extra spaces either at the beginning or at the end, and that's why I'm using x.strip. Alright, so after that you have your new label column, and these are those unique numerical values for your 7 categories. So for example, technology now is represented by category or label number of 0. Similarly, the spore, SPOR, is represented by this numerical value of 1. And next, I am just building a quick pie chart. This is almost kind of mandatory when you are doing multi-class classification, that how your data is distributed across various classes. So I'm just using category.valueCounts and then plot kind pie chart, and that's my pie chart. As you can see that almost all 7 of the categories are almost equally distributed. That is, all of the categories are equally represented in my data set. This is a very well balanced data set. And the next 2 cells are the all important tokenizer and model declaration. So the first one, this tokenizer variable is applying BERT tokenizer fast, and then from pre-trained, and I'm applying these particular pre-trained model that we'll be working with, BERT based Turkish uncased. And then in the next cell, I am defining an instance of my pre-trained model, which is BERT for sequence classification dot from pre-trained. And to that I'm passing our number of labels, which are our num labels. We have already defined our num labels to be, I think that's just a number of individual classes I have defined earlier. That's 7 of them really. All right, now an ID2 label, which is our ID2 label, and label 2 IDs as well, and then passing the model to your device. That could be CPU or GPU. And after you do execute these 2 cells, you will get a very long output detailing all these various layers and individual internal components of your model. That is, in this case, BERT sequence classification. Now let's quickly go through some of the useful information and some of the understanding that you know about the model when you go through these long output of the various layers of the model. So first, about the model components. The model consists of several components such as embeddings, that is word, position and token type embeddings. Then encoder layers, we have 12 layers in this case, each with self-attention, intermediate and output components. Then layer normalization and dropout layers for regularization, and also GALU activation function used in the intermediate layer. And about the model dimension, word embeddings. The model has an embedding size of 768 dimension and a vocabulary size of 32,000 tokens. Then position embeddings. The model can handle input sequence of up to 512 tokens in length, which we passed when executing the model instance. Then about the encoder layer, the model has 12 encoder layers, each with a hidden size of 768 and an intermediate layer size of 3072. And the task specific classification layer. So the BERT for sequence classification model is designed for sequence classification task. It takes the final hidden state of the CLS token and passes it through the linear layer and a softmax function to produce class probabilities. In this case, the model is configured with a custom number of labels, which is 7, which we passed as one of the input to the model as num labels, and label mappings, that is ID to label and label to ID. Now let's understand the flow of raw input text through the pre-trained BERT model, and finally coming out on the other side of the model as a class prediction in the context of these task-specific fine-tuning. So in BERT-based model like what we are using here, BERT for sequence classification, the CLS token, that is short for classification, serves as a special token that is prependent to the input sequence, and it is designed to be used as an aggregate representation of the entire input sequence for classification task. Here is a step-by-step breakdown of how the CLS token is handled during the fine-tuning for a specific classification task. So the first step is tokenization. During the pre-processing of the input text, the tokenizer inserts the CLS token at the beginning of the input sequence. For example, if the input text is this is a sample sentence, the tokenizer input would look like CLS, then this is the sample sentence. And then embedding the tokenized input sequence, including the CLS token, is passed through the BERT model's embedding layer, which converts the tokens into continuous valued word vectors. And then the encoder layers, the embedded input sequence is then processed through the BERT model's encoder layer, which consists of self-attention mechanisms and feed-forward neural networks. During this process, the model learns to capture the semantic and syntactic information present in the input sequence, as well as any relationships between the tokens. And the final hidden state of CLS will come after this. So at the end of the BERT model's encoder layer, each token has a corresponding hidden state vector. For the CLS token, its final hidden state is used as an aggregated representation of the entire input sequence. This vector is then passed to the task-specific classification layer. And then the linear layer. The final hidden state of the CLS token is fed into a linear layer, which maps the 768-dimensional vector to a vector of size equal to the number of target classes. In this case, for our exercise, it's 7 classes. And this is essentially a weight matrix multiplication followed by a bias term addition. And then softmax function. So the output of the linear layer is then passed through a softmax function, which converts the raw output values into class probabilities. The softmax function ensures that the sum of probabilities across all classes equal to 1. And finally, prediction. The class with the highest probability is chosen as the final prediction for the given input sequence. So to sum up the overall flow, during the task-specific fine-tuning, the model learns to adjust weights and biases based on the training data and the target labels. This involves updating both BERT model's pre-trained parameters and the task-specific classification layers parameters through backpropagation and optimization techniques like gradient descent. And this fine-tuning process allows the model to adapt to the specific classification task and improve its performance to the given dataset. Now, a common question that you may ask is, in this task-specific fine-tuning, do all the weights of the pre-trained BERT model gets modified during this fine-tuning process, or only some of the weights gets modified? Well, during a task-specific fine-tuning, all of the weights of the pre-trained BERT model are potentially subject to modification, including the weights in the embedding layer, the encoder layers, and the classification layers. However, the extent to which each weight is modified depends on the learning rate, the specific task, and the training data. In general, fine-tuning a pre-trained model like BERT involves updating its weights to better adapt to the target task. When fine-tuning begins, the initial weights of the model come from the pre-trained model, which has already learned general language representation from a large-scale unsupervised task, for example, master language modeling. And during the fine-tuning, the model is exposed to the particular task-specific training data and labels, and the weights are updated using backpropagation and gradient descent. Typically, the learning rate for fine-tuning is said to be smaller than the learning rate used during pre-training. This is because the pre-trained model already has a good understanding of language, and the fine-tuning process aims to make small incremental adjustment to the weights to adapt the model to the specific task without losing the valuable general language knowledge that the model had already acquired during its pre-training phase. Alright, next step is to split the data set. So I'm doing it rather manually here by taking the size of the entire data frame and then From that size, I am splitting the train, validation, and test set by using the slice notation of an array. All right, next I need to apply the tokenizer. We already have defined the tokenizer before here. That is, let me quickly check. Yep, that's our tokenizer, and that tokenizer need to be applied on all the three sets. That is train encoding, val encoding, and test encoding is the result of the output after applying the tokenizer. And then you have to define your data loader. Very standard and simple code here. That is, you have a get item method and a len method. Only important line to check here is this line within my get item method. So here I'm using a dictionary comprehension that constructs a new dictionary called item. And this line converts the encoding values associated with the input text at the given index IDX into a PyTorch tensor. So this particular part, self.encoding, is a dictionary containing tokenized input text with keys like input IDs, token type IDs, and attention mask. These keys represent different aspects of the encoded text that are needed for processing by the BERT model. The values associated with these keys are list or arrays of integers. And then I'm applying these items method on encodings on self.encoding. So items is a method that returns a view object displaying a list of a dictionary's key value pairs as tuples. The dictionary comprehension iterates through the key value pairs of self.encodings with the variables key and val. For each key value pair, it creates a new key value pair in the item dictionary where the key remains the same and the value is a PyTorch tensor created from the elements at the index IDX of the original value. And that's what you see. That is, this key that I'm getting from self.encoding remains my ultimate key, that is resultant key. But the val that I'm getting from self.encoding, that gets transformed to a torch.tensor. So in essence, this particular line of code is converting the relevant parts of the input encodings, for example, input IDs, attention mask at the given index IDX into PyTorch tensors and storing them in the new dictionary called item. This format is necessary for input to the BERT model during training or evaluation, and you will see this pattern in almost all pre-trained Hugging Face model. And once your data loader class is defined properly right here, you can just invoke this class to create your train data loader, val data loader, and test data loader. So now you are completely ready to do the actual training. So that's the reason now you need to define your training configuration. So I import training arguments and trainer. And also before the training, I need to define this function compute matrix. It's just a standard computation matrix that this method will return. The compute matrix method takes spreads as its argument, and then in this line right here, it gets a pred.prediction values, and then on that it applies argmax. So this numpy argmax method returns the index of the maximum value along a given axis. In classification problem, we are interested in finding the class with the highest probability for each observation, and that's why argmax is the one that we need to use here. And the -1 inside the argmax represent the axis along which the operation should be performed. In Python, negative indices are used to access elements from the end. So -1 here means the last axis, which is a column in a two-dimensional array. So with this line, I have the maximum predicted value as preds. And then because I have the preds, I have the actual labels, I can actually calculate the precision, recall, and F1 score by applying this scikit-learn method here. And that's exactly what I'm doing. And also I'm calculating the accuracy by again using accuracy score method of scikit-learn. And the compute matrix just returns these accuracy, F1, and precision and recall as a dictionary. All right, and next is defining all my training configuration. So you can define your output directory, And then the important part is number of epochs, then weight decay, warm-up steps, all pretty standard things. And this definitely is subject to experimentation. You can, of course, run up to 20 epochs or 50 epochs to check how your accuracy scores are improving or not. And yeah, so let's proceed. After your training configuration is done, you also need to invoke the trainer class here, where your model is a pre-trained model that we have defined earlier. And arguments are my training arguments, and then train dataset, eval dataset, and compute metrics. And right after that, you just do trainer.train. This particular cell will take some time, maybe half an hour or so for running 3 epochs. And then before going further, I also need to define my predict method, which will predict the class label for a given input text. And the first step is obviously you need to tokenize your input text, and that's why I'm using tokenizer here. And next you get your outputs by passing the inputs to the model. All right. And next, take a note of this particular line, because there are a few things within it. So I get my outputs, I take the 0th element and apply softmax on that. And here I take the 0th element because the BERT model returns a tuple containing the output logits and some other elements depending on the model configurations. So in this case, the output logits are the first element in the tuple, which is why we access it using outputs and then 0. And this output 0 is a tensor containing the raw output logits for each class. The shape of the tensor is batch size by number of classes, where batch size is the number of input samples. In this case, 1, because we are predicting for a single input text, and number of classes is the number of target classes, which is 7 in this case of ours. And then softmax 1. The softmax function is applied along dimension 1, that is the class dimension, to convert the raw logits into class probabilities. Softmax normalizes the logits so that they sum to number 1, making them interpretable as probabilities. And here in this line, I'm just mapping the predicted class index to the actual class label, because we already have defined our ID to label, which means that given an ID, we can find out the label as easy as this. And then finally, from this predict method, I'm just returning probs, pred label ID X, and the actual class prediction. And next, I'm just saving the model by passing a model path and then reloading the saved model before doing my inferencing. And these are standard, so you use save model method and then save pre-trained. And before the inferencing, I am building a pipeline and naming it as NLP. And my pipeline is sentiment analysis. My model is model, and tokenizer is tokenizer, which are all defined right here. All right, now I can do my actual inferencing. So here I am doing the actual inferencing. So this is a Turkish statement, right? It's a sentence in Turkish language, and which actually means today the weather is very nice. I want to go for a walk outside. I got this translation from doing an internet search and also checking it with Google translation tool. And so I am passing these to my NLP pipeline, and the purpose is that NLP pipeline should tell me the class of these with a probability. So this is the output that you will get, that the label is SAG-leak and score is 0.829, pretty high score. And SAG-leak is a Turkish word that means health in English. And as you can imagine, that this whole sentence, that today the weather is very nice, I want to go for a walk outside, it's kind of denoting the health concept. Next inferencing, I'm taking here again, this is a Turkish sentence, and actual meaning of this in English is deep learning and AI is going to change the world. And the NLP prediction on this is label is technology, score is 0.9932, very, very, very high probability. And that's absolutely right. And the third one, inferencing, again another Turkish statement, the meaning of which is Due to recent volatility in the economy, the stock market index has been at quite low levels. And as we can see from the inference, the level is economy. Score is again very high, 0.98, which is obviously this is an economic news, and that's exactly what the model predicted. Alright, that's a wrap for this video. Do stay tuned because I am planning to do many more transformer videos over the coming weeks. So thank you very much for watching and see you in the next one.